Huh?
Oh, I slept.
You slept through the whole thing? I did not. My dog woke me up at 3 a.m. All right. We're good with this part? Yeah? Okay. Let's turn to the next page. Now, in solution, you will never find a hydrogen ion alone because hydrogen ions are extremely reactive. Okay, so what happens is hydrogen ions are actually going to immediately combine with a water molecule, and then they will produce something called the hydronium ion, which is H3O plus 1. You should know this concept. You should know that hydrogen ions, since they immediately combine with water to form hydronium, hydrogen ions are the same thing as hydronium ions, right? So whatever the concentration of hydronium is, that is the concentration of hydrogen ions in solution. Okay? Okay. Let's look at another example. So let's come down here. I don't have that much room down there, so I'll use this reaction here instead. When I partner up NH3 with NH4 plus 1 on the right-hand side, you can see that we're going from H3 to H4. So here we are gaining or accepting a hydrogen ion from something else. That's why they wrote base underneath NH3. Its partner on the other side would be called the conjugate acid. And you can abbreviate it as C period acid. Okay? And then I'm going to partner up this H2O with OH negative 1 on the right-hand side. And you can see that we're going from 2 hydrogens to 1 hydrogen. So that means here we are donating or losing a hydrogen ion to something else. That's why they wrote acid underneath water. Its partner on the other side would be called the conjugate base. You may write it as C period base. Okay. And something else that they're going to introduce here is the concept of conjugate acid-base pairs. The definition is at the bottom of the page. Conjugate acid-base pairs differ by 1 hydrogen ion. So that means you have 2 conjugate acid-base pairs here. The first one would be my NH3 and NH4 plus 1. And then the second one is H2O and OH negative 1. Okay. All right, let's take a look at the next page. Let's look at the sample problems that are on the next page. Are we good with this? Okay. Okay. I'm going to skip number 1. I'm going to go to number 2. Here they've given us a column for the conjugate acids and then a column for the conjugate bases. When you're writing the conjugate bases of substances, you want to remove 1 hydrogen ion and bring the charge down by 1. Okay, so that's if you're going in this direction. So if I remove a hydrogen from H2C2O4, what do I get? And then since I'm neutral here, there's no charge here, this would come down 1, so this would now be a negative 1, since I lost a hydrogen ion with a positive charge. And then for HCO3 negative 1, if I remove a hydrogen, what would I get next?
CO3 -2.
Yeah, CO3 -2. Since this was -1, this came down to -2. So that means if I'm going in the opposite direction, I would add a hydrogen. So if I'm going this way, you're going to add a hydrogen, and then the charge needs to come up 1. So this would become what?
HSO3 -1.
Yeah, and then this one would become H3O plus 1. Okay. Sometimes they're going to ask you to complete the equilibrium, and they would give you 2 reactants, and then they want you to identify the conjugate acid-base pairs. So if you take a look here, you can see that NO2 -1 doesn't have a hydrogen to give up, so that there's no way for it to be an acid. Does that make sense? So that means over here, this must be the acid because it has a hydrogen that it could give up. So that means it would become, I'm going to keep them in the same order, HCO3 -1. So the hydrogen would be moving in this direction. That means this is the base because it will accept a hydrogen. It will become HNO2. And then the partners on the other side, this would be the conjugate acid. This would be the conjugate base. And then in terms of the acid-base pairs, you could highlight them in the same color. So this is one acid-base pair, and then this is the other. Okay. And then let's turn to the last page where we have the practice problems and amphiprotic substances. Okay, I'm going to skip number 1 and number 2 and number 3. I'm just going to go straight into amphiprotic, and then we'll be done with this. So water has the ability to accept or donate a hydrogen. That means water can act as an acid or a base. So in this example up here at the top, you can see that we've got water donating a hydrogen to ammonia, so it's acting as an acid. And over here, we have water accepting a hydrogen from HF, so that means it would be acting as a base. Anytime you have something acting as an acid or a base, we call it an amphiprotic substance. Water is a very common amphiprotic substance. You should know that. You should also know that many anions, those would be polyatomic ions with negative charges that contain hydrogen. They also have the ability to act as amphiprotic substances. So, just want to make sure you understand that anions have got a negative charge, and they have to contain a hydrogen ion. Otherwise, they can't be amphiprotic because they wouldn't have a hydrogen to donate, okay? Some examples of some common amphiprotic ions are listed here. Notice they are all negatively charged and they all contain hydrogen, okay? So let's take a look at the quick check and then we're done. Let's look at number 3. They want us to circle the amphiprotic substances on the list. Okay, look at A. Would A be considered amphiprotic? No, you're right. Why not?
It's not negatively charged.
It's not negatively charged. It's acetic acid. How about B? Yes. We got a negative charge here, and it contains a hydrogen. So, yeah, B will work. How about C? No. Doesn't contain a hydrogen. D? No, doesn't have a negative charge. How about E?
Yes.
Yes. E has got a negative charge and a hydrogen, therefore it works. Okay. Okay, this homework